So I think this dimension is very important. It doesn't really matter how exactly it is organized, but it's more, to make sure that it is taken into account. So the second dimension is a more operational dimension, and is to consider what type of approach the teachers are going to use. Are they going to develop a fair, and this is going to be their objective of the year? Are they going to have a production of an object, like biosensors? We had an example yesterday, and they're going to team together to build these biosensors and use it then in biology. So what strategies were they going to adopt? And usually there was a balance to find between a more inquiry approach and a more project-based approach. And depending on the teacher, because in the team usually one of the teachers would lead more the project. If, for example, if the technology teacher was more involved, it tended to be more project-based orientated projects. But it doesn't really matter. What was important is how the team constructed an operational way of interacting together. And then the third dimension usually was quite left out. And the third dimension is more an epistemological dimension to have a very deep consideration on what does it mean to connect these pieces of knowledge. What senses does it has? It's not just a question of making sure that the students work together with this, but how it relates to a stronger or deeper understanding of one specific topic. And for example, there was some discussion about energy, and I have a strong discussion on, in chemistry when we talk about energy, or in technology when we talk about energy, usually we don't talk about the same thing. And this is something that usually the teachers needed external help with this, needed a mediator to help them, because it is not something that can be solved in a team with the technology teacher that says, oh yeah, energy is like that for me. So this is something very deeply that usually missed in the projects.
Yeah, it's very nice. So we should consider the three dimensions when we organize any STEM education activities.
This would be a suggestion.
So may I add? Yeah. So maybe I can draw your attention to a meta-analytical study published in 2004 in Proceedings of National Academic Science. So that study by Freeman. So that study actually collect 225 studies in undergraduate STEM education. So the most important factor in terms of having an effective program is active learning in a STEM class, because right now traditional lecture class still prevail. I think in undergraduate, maybe also in K-12 all over the world, I think. So in this study, actually, the meta-analytical study, they actually compare all those studies, and they found out if you use the active learning approach, including problem solving, inquiry, project-based learning, all that, more active learning actually increase student achievement scores in undergraduate scores and the concept inventory, concept acquisition more effectively. So this is one of the studies maybe we can refer to.
Yeah. So you already mentioned about the touch questions, the methodologies. So it can be 6A's models, or it can be project-based, problem-based, and also we can facilitate the interactive learning environment with classroom. Also, traditional classroom is still a lot of live interaction. So we talk a little bit about the content. The two TV projects already work a lot on the content of STEM module. So the question is, what kind of contents are relevant for STEM activities? before Juan mentioned it should be linked to the industries and should be linked to the real life experience, but it's still a little bit general. Yeah. And in Vietnam, we think it's somehow sort of related to the content of the curriculum as well, because the time in school is a constraint, so we should go too far from the content of the curriculum. So, Chang or Hong, your members Stanford TV, can you comment on some hint, advice to select the content for STEM activities?
So we also, that project actually we conducted for the past 2.5 years. So it's actually, we try to, of course, develop some, first of all, we try to fit students' needs in the classroom. So right now, we actually implement in the junior high school classroom instead of a senior high. The reason is we try to find a common target audience. So it turns out among those 3 countries, so these are the appropriate grade level, 7th, 8th grade students. So the 9th grade students are impossible because they need to take an entrance examination. So now you need to experiment this instructional module. So for that instructional module, we actually use, of course, the active learning approach. So the lecture is very limited. So we try to leverage on our platform, the Cloud Classroom. So it's a series of question-driven based activity. So for each question given to the students, then they need to do some hands-on activity to work on the problem. Then they need to reflect on that. So it's very, I would say, very inquiry-based. So as a result, of course, we found that students, their performance increased, the achievement score increased. But the regular classroom, if you really drill practice, you can also get the same result. But however, this module actually, we believe, actually interests students in doing science. So this is a very important feature in terms of this project results. Okay. And we actually also increase students' interest in STEM topic, and also increase their develop their inquiry skills and also achievement scores. So it's quite universal among 3 different countries. So this is why maybe in the future we try to maybe, of course, the sustainable things. If the project funding cut next year, I mean, if that Ministry of Education, Science and Technology doesn't fund anymore, we will probably try to seek other fundings in order to sustain that. So this is quick reply.
Yeah. So we already discussed so far some elements of any STEM curriculum which should be effective. And thinking about curriculum, we also think about the condition for it to be successful. And we have metaphor of spider web curriculum that we manufactured, if you can see on the screen. So it's not the curriculum itself, but also the other condition. So think about the facility, equipment, materials, and also think about teachers, of course, very important. And also the other school partners. So can you discuss a little bit more about the facility, for example? We should facilitate school with a lot of equipment, but it's not the real case, it's the ideal case. So what can you think about the minimum equipment and materials? And also relevant, of course. And also think about the teacher standards, teacher professional development, which prepare for successful, effective STEM education. And also how about the other partners like university, you mentioned, industries, and parents as well can support that.
Sorry for the messing around, I just ran out of power. But, the minimal equipment, I think, for science and invoking curiosity is nature and a ball of string. I think you really don't need very much at all to be able to excite students and help them understand basic principles. We're never going to have in classrooms or in schools the high-end equipment that the industry has. So that's where it's really important to have those connections with industry so that you can engage students directly with them. Of course, funding is wonderful. And it's more difficult in areas such as technology, I would imagine, to keep ahead of what students need to know with minimal equipment. You probably can't do too much in the area of technology with a walled string, but certainly for general curiosity and engagement with scientific and mathematical principles and engineering indeed, you don't need very much at all, to my mind. You just need a particular enthusiasm and approach. But that's my perspective.
Yeah, so meaning an environment will focus more on the teachers who can encourage the curiosity of students and support and nurture success curiosity.
I will follow the Australian line, and you talked about the teachers and what do the teachers need, and we've been talking about curiosity a lot, and I think one key element in the teacher's development is how to also consider the teacher's curiosity, and sometimes maybe we forget about that, and we think about, you know, having interaction between the students and university lecturers or people from companies and enhance their curiosity, but how do we do in initial training to also have these interactions? And you talked about teachers that had previous industry experience, and I think this is a very good example. We actually had some discussion a few years ago in France into considering that teachers during their initial training should do also internship in any type of company, whether, you know, from nursing to engineering, or and it was a very nice idealistic idea that we have not been able to bring in a concrete manner, because the teachers are already doing quite a lot of internship in other schools, and it doesn't fit in the time that we have with the teachers. But I think this would be a very interesting I keep thinking that it would be a very interesting idea to consider that to be a teacher, to have at some point some experience or some vision of how it is in another job